Hi everybody. Okay, today what I'm going to be doing is trying to explain and to demonstrate a common mode noise in antenna systems. What it is, why is it there, and how does one sort of cure it? Okay, before I proceed with the practical demonstration, I have to do a bit of a theory. This picture represents a coaxial cable, basically. Okay, this would be, say, coaxial cable connected to a dipole or any antenna for that matter. But nonetheless, let's assume it's a dipole. You got basically a center conductor, and we can see the current flows, say, one way. And then, of course, over here we got the outer shield, which is the screen cable. And you can see the current also flows into the other element of the dipole or wherever antenna in the opposite direction. Now, it is fair to say or imagine the equal and opposite currents are flowing in both sort of wires. When such a condition actually happens, the fields generated around these wires would be equal and in an opposite direction, and they will actually cancel each other. But when the imbalance occurs, okay, then of course the conductors, one conductor will carry more current than the other one, type of thing. And this additional imbalance, should I say, will actually cause a magnetic field around the wires, and the currents won't be cancelled, and the actual wires will start to actually radiate along the actual coaxial cable. Now, the outside shield is usually the culprits, okay? Now, I have to go a little bit back in sort of theory. Now, in RF currents and voltages, imagine a solid, say, center wire, and then you get the screen cable, okay? Now, if you can imagine that screen cable around the center conductor, which is isolated from screen, of course, although it's very thin, it has got a very, very small thickness. But nonetheless, due to it's called a skin effect, in RF sort of currents, they usually tend to imagine this is wire. Okay, now although it's very thin, still that wire, I'm just going to magnify it, still has got a big mess. Now let's imagine okay, that on that screen cable, you will get the currents because they're flowing on the surface of the actual any wire. And in this case, it would be the surface of the actual screen cable, type of thing. So you will get the inner, on the inside, looking at, say, from this side, looking at from this side, you will see on the screen cable, the currents will flow that way. But due to the skin effect, where the currents, especially at higher frequencies, bigger than DC, the currents, they tend to travel only on the surface of the actual conductor. And of course depends on how strong is the actual current flowing through, the RF current and so on. But it never really occupies, the full it's usually usually on both sides of the screen. As I said, it's a magnified screen. Although very thin, as I said, the actual mesh, it's still, it will travel on both sides of the screen. And this is what's actually happening. If you look at it, that's the inner side of the shield and that's the outer side of the shield. Now, this current on the outer side of the shield, okay, it's actually acting as an electrical third conductor, because you got 1, 2 for a dipole, and now this third outer shield or whatever will actually act as a third conductor. Now, that third conductor will cause severe distortions of the patterns of the actual antenna. It will change the impedance, the SWR, and it will also radiate and receive unwanted signals. So sometimes it can cause a havoc to electronics, to people, and in high power transmitters it can actually cause even RF burns, especially near radios and things like that, or near antennas. When I say RF burns, sometimes when you transmit, you touch any metal object or whatever, it actually shocks you. So it can be quite dangerous and hazardous, let's put it that way. Now, basically, how do we actually solve it? Solving it, first of all, we have to remove this. Okay, now this imbalance is and flowing of the current on the outer skin of the, besides the inner sort of current on the conduct of the actual screen around the coaxial cable. This outer sort of current gets generated due to the skin effect and also due to the not properly tuned antenna, maybe nearby sort of metal object next to your antenna. Many various sort of things will actually cause it. Mismatch between the antenna and the actual transmitter and things like that. And that's what actually causes that and intensifies the actual current on the outer shield, which creates a third leg, as I said, which acts as an extra element and detunes your antenna altogether, which is no good. Now, the aim is to actually reduce these currents flowing on the outer shield. How do we do it? Very simple, okay? And that would be using a balun, okay? A balun is a device, basically, a coaxial cable is unbalanced and the antenna is balanced. So basically what it does, it matches up balanced to unbalanced type of thing. And in that way, you actually introduce a high impedance on the outer shield of the actual screen of the coaxial cable. And that way, your antenna, if properly tuned and whatever, will actually perform and exhibit the actual field pattern that was designed to do, type of thing. And the impedance will be stable, the SW will be good, and of course, because there is no interference with the transmission, the full power will be most of the power will be transferred into the antenna, not lost through a third conductor and mismatch. Basically, you will get more radiated power out of your system or receive more. Also, your coaxial cable and your antennas will be less susceptible to the actual noise and interference and things like that. So now, what is the balun? Balun can be made out of wire, copper wire, can be made out of coaxial cables, can be ferrite sort of clip-on, or ferrite toroids can be used. These various also filters can be made to reduce, and the aim is to reduce that current flowing on the outer sort of shield of the screen wire. Now, basically, what I'm going to do is to do the demo. I've got a simple sort of setup. I've got the portable radio here, which I'm going to transmit a bit of a power. I've got like a field strength meter, which we can see that, the power is coming through. And of course, the cable, I got a coaxial cable, okay, which is connected to the actual antenna. It's connected over here, okay? And this is actually my antenna. Let me do it. If you look at it, I got it hanging from the actual ceiling, okay? And over here, what I have done is I've got my pickup coil, okay, which is now connected basically into the instrument, okay? And we will actually measure over here and see what type of, and by how much we're gonna, and how we're gonna reduce the actual currents flowing on the outer basically layer of the actual cable, of the actual screen cable. Now, okay, on that note, let me go and then let me try and sit over here so I do not interfere with the antenna. What I'm gonna do is I'm gonna zoom onto the instrument, okay? Let me just do this, okay? Now, I don't know if you can really see, but nonetheless, if you look at it, that's about 35, somewhere around there, 35, okay, 35. I'm just going to write it down. Okay, so we measured